Hi again everyone, Chris Tisdell here. In this presentation I'm going to discuss the equivalence between a Cauchy problem involving partial differential equation and an integral equation. Now here C is a constant, G and H would be known functions, and we're asked to show that this Cauchy problem, or this initial value problem, is equivalent to this integral equation. So before we get down to it, what does that actually mean? Well, it means that every solution to problem 1, 2 satisfies the integral equation, and every solution to the integral equation satisfies equations 1 and 2. Okay, so it's a two-step process to solve this problem. One step involves assuming U is a solution to 1, 2, then show that the integral equation holds, and then you go the other way. You assume U satisfies the integral equation, and then you show that 1 and 2 both hold. So I'm actually going to start with the integral equation and move to this, and then I'll prove it the other way. Okay, so firstly, let's just check the initial condition. Okay, so if I go here, so let star hold on this set, we have the following. Well, if I plug in t equals 0, I'll get h of x here, and integrate from 0 to 0, that's 0, so it's pretty easy to see that all we're left with will be h of x. Okay, thus 2 holds. Okay, that was pretty easy. Let's have a look and see if 1 holds. To do this, we have to compute u sub t and u sub x, and here c is a constant. Okay, alright, now to compute these partial derivatives we need to differentiate this term and this integral. So what we're going to do is apply an idea called Leibniz rule for differentiating under the integral sign, and I have lots of other videos on this, but so let me just step you through it. So Leibniz rule for differentiating under the integral sign, we obtain the following. Okay, so the easiest differentiation to do first is u sub x du dx, because there's no x's in the integral sign. It turns out that means it's a bit simpler to do. Okay, so if I differentiate this via this term first via the chain rule, it's just this, or we just write it down. Okay, and then we have to differentiate this integral somehow. Okay, now Leibniz rule basically says that you can take this operator and shift it into the integral sign. So you'll get you'll be differentiating the function g partially with respect to x. Okay, so now I'm applying Leibniz rule. Okay, so what we have to do is differentiate this composite type function partially with respect to x. So how do I do that? Well, you may just be able to write down the answer, but if we let, say, Q be this, x plus s minus t times c, remember when c is a constant, then we have g is a function of q and s. And if you apply the chain rule here, so let's just start up here. G depends on q and s. Q depends on x, s, and t. And remember, c is a constant. What we can do is form a chain rule. So to calculate dg dx, you find all the roots from the top to an x. So, and when you go from letter to letter, you form a derivative. So dg dq times dq dx, so q's up here. So g sub q times q sub x. Okay, so okay, so g sub q, well, we don't know what that is, but q sub x, that's just going to be 1, right? So okay, I'm just going to omit the argument here, just to save a bit of space. Okay, so that's about as far as we can go with this derivative. So let's go and now differentiate my expression here with respect to t. Now this is a little bit harder than the case where we were differentiating with respect to x, because we have a function of t in the integral sign. That just means an extra term is added to our differentiation. Okay, u sub t. So I've differentiated this with respect to t, again by the chain rule. I'll get something like that. Plus this. Now again, Leibniz rule says yes, 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 let's move that in, but we need to remember to check if there's any functions of t in the integral sign. There is in this case, so that adds, there's one constant which doesn't change anything, and there's one function of t, which is just the t function. So in that case we have to add an extra term in. Okay, so it'll be the derivative of this term multiplied by the function evaluated at t. T. Okay, so that's the extra term that we get here, and yes, let's just move the derivative, or the operator, into the integral sign. Okay, so now we want to differentiate this with respect to t partially and clean this up a bit. Now, I'm not going to redo the chain rule for this one, you can do it yourself, but essentially what are we going to get? We're going to get this c coming to the front. Okay, so that'll be 1. That will just be x comma t. And yes, we differentiate with respect to t, so it'll be -1 times c coming all to the front, where you can, if you like, you can have the same variable q here for that part of the argument. So it'll be g sub q. Okay. So we've got these terms for our u sub x and these terms for our u sub t. We're almost finished now. All we need to do is take these two terms, plug them into the left-hand side and see if we end up with g. Okay, so left-hand side of our PDE is the following. So let's take this and multiply that by c and add them together. So I'm just going to suppress the arguments here to save a bit of space. Okay, that's that one, plus c times all of this. Okay, hopefully you can see now that if I expand this, everything's going to cancel out except for the g. Okay, so that is step one of our problem. We showed that every solution to this problem satisfies this and this. So let's make a conclusion. Hence, all solutions to star satisfy 1 and 2. Okay, so we've shown that every solution to the integral equation must satisfy this initial value problem. So now let's go the other way. Let's assume u is a solution to 1, 2 and come up with this integral expression here. Okay, let u be a solution to 1, 2. Now I'm going to define a new function here, z. Okay, z via the following. Okay. Okay, so here we're introducing this parameter s and fixing x and t, and looking, well, I guess defining z as the solution of this evaluated along a line. Okay, so that line, think of the vector c, comma 1, and think of a line that's parallel to that vector, and say here's the origin over here. Oops. Okay, a bit of a bad drawing there, but okay. And to get to any point on the line, it's just this vector plus a scalar multiple s of this vector here. So you stretch or you spin or you compress and you get all points on the line L. Okay, so what this definition is about is looking at the solution to this problem just on this line, which itself will be a function of one variable, s, a curve. Okay, so if we define a z in that way, let's differentiate it. Now, for this, you may be able to do it straight away, but let's look at the chain rule. Okay, so for the chain rule, sometimes I like to draw just little diagrams. So if we let Q be x plus SC and R be T plus S, where x and T are fixed, then use a function of Q and Q is a function of S and R is a function of S. So to differentiate this with respect to S, just go down the paths to an S and when you go from letter to letter, you form a derivative. Okay, so it's going to this is going to be U sub Q times Q dq ds. Now dq ds, C is a constant, remember, it's just going to be C plus the other path, du or U sub R times dr ds. So dr ds is going to be 1. Okay. All right. Now, if we compare this with this and just sort of, replace x with q and t with r, you can see that it is just the following. Okay. So, what I'm going to do now is integrate both sides using the fundamental theorem of calculus. Okay, FTC means fundamental theorem of calculus. And we have the following. Okay, so I'm going to integrate from minus t to 0, and be apparent why that's useful in a minute. Okay, now if I write q and r again back in terms of s, I'll get the following. Okay, so this, well, it's not exactly looking like this yet, but at least we've got a g as our integrand, so maybe we're heading in the right direction. So on the left-hand side, we have z of 0 minus z of negative t. On the right-hand side, well, I'll just leave it as it is for the time being. We're going to simplify it or clean it up a bit in a second. Okay, now what is z of 0? Well, z of 0, put in s equals 0, it's just u of x comma t. If I take this to the other side, what is z of negative t? Well, when s equals negative t, that's 0, and this becomes x minus ct. Okay, so this is invoking the initial condition now. It'll just be h of x minus ct. Okay, so before I write this down, look at what we have now. We've got that term and that term. So it looks like we're pretty close to this. All we have to do is get this now. Okay. So how do we do it? Well, just a substitution or change of variables here. I'm going to let v equal s plus t. Okay. So dv is going to be ds. And just adjusting limits of integration, when s equals negative t, v will be 0. And when s equals 0, v will be t. Okay, so taking these and substituting into the integral, we'll get the following. Okay, so when we sub in, we can rearrange here and get rid of the s. And I'll just be left with, sorry, there should be a v there. Okay, and I'll be left with just v there, dv. Okay, And this actually is exactly what we wanted, except I've got V's instead of S's. So let's go back to the S's, and we've got exactly what we were asked for. Okay, because V, S, it's a dummy variable. It doesn't really matter what it is. Okay, so we have star. So what do we conclude? Thus, every solution to our initial value problem satisfies star. And there you have it. Okay, so when proving equivalence between initial value problems or boundary value problems and integral equations, it's a two-step process. You start with one of the expressions and you show that you can get to the other expression. And then you flip it around. You start with the other expression and go show that you can get the other expression. Okay, so here we, in the proof that I've just done, when you couple them together, we showed that every solution to this problem satisfied this, and every solution to this problem satisfied this. Okay? Now, in other videos, I'm going to show you how to apply this kind of representation to generate solutions to particular problems. I hope you can join me for those presentations.